Today we're still studying double integrals, but we're going to take a look at double integrals where the region is better defined in polar coordinates than it is in regular Cartesian coordinates. So to summarize what we have so far, we have the very first double integrals that we did were coming from square regions. And if you can remember that whenever we did square regions, I don't know if you guys realize this or notice this, but in Cartesian coordinates, when we're dealing with rectangular regions, your limits are all constants. And that's because, I mean, we want to also think of Cartesian coordinates as rectangular coordinates. And whenever we're dealing with constant limits for our double integrals, it's going to be the shape of a rectangle. So sometimes, instead of saying Cartesian coordinates, I refer to this as rectangular coordinates. And when we do have a rectangle in rectangular coordinates, then your limits for your double integrals are going to be constant limits. From there, we took it to another level where we're looking at general regions. In the book, I think, or in most books, they call these regions type 1 and type 2. I don't really remember which type is which, but one type goes through the x values first. So a region of what I'm calling type 1 might be something like this, where you have two functions, x is equal to g2 of y, and then x is equal to g1 of y. And they are, they're going to be your inner limits of integration, so that when you draw a line parallel to the x-axis, you're going to enter through g1 of y and then exit through g2 of y. Yeah, this is when we're dealing with respect to x or y first. Or in this case, we're dealing with respect to x first. And then with respect to y is our second outer integral, and the outer limits are going to be constants. And then the other type would be kind of just switched around. Where you would be integrating with respect to x or with respect to y first, going into some f1 function, and then getting out of some f2 function with respect to y, and then the outer limits are constants a and b. So these are the regions that we've been looking at before that we should be kind of used to by now. The rectangular regions are easy to work with. They're going to have constant limits. And then the other general regions, well, it'll depend on what you want to integrate with respect to first, x or y, and then that'll determine which type it is. Okay? So that's the stuff that we've done already. Now the question is, what if we had more complicated regions, or more directly towards what we're talking about today, what if you had regions that are polar in nature? Okay. Now, the first example over here is something that we could probably handle in Cartesian coordinates. So let's say for this one, in Cartesian coordinates, say we wanted to integrate with respect to y first. We would draw a line parallel to the y-axis. That means we have to come up with these equations of this circle from the top half and the bottom half, or I guess from the bottom half to the top half. And so you would solve for a y value equals, and then if you take the square root of this, 1 minus x squared, you're going to deal with a positive and negative. And if we're dealing with the bottom part, we're talking about the negative half of that circle. And then on the top over here, you have y is equal to the positive of that square root. So then your limits of integration will end up being, with respect to y first, going from negative square root of 1 minus x squared to positive 1 minus x squared. And once you got that figured out, your outer limits are going to be constants, so all I would be looking for are the numbers where it stops and starts and stops. And so I would go from negative 1 into x, and then positive 1 ending here. So as you can see, it's doable. I mean, the functions certainly don't look pretty and probably will not be very easy to calculate, but it's still doable. The next one would be a little bit more challenging. We can do things with respect to x or y first. Let's pick one just to show you that they're both going to be difficult. Integrate with respect to what first? No, x or y? What? X. Let's integrate with respect to x first. Now, if you integrate with respect to x, remember the technique is to draw a line parallel to the x-axis. Now, I'm drawing several lines because things are going to change as we move along this thing. So if I integrate with respect to x first, I'm actually going to have two different areas that I have to consider split up here with respect to x first. I would consider this area, and I would need to go in through an x value of, and I'd solve for x here. X is equal to plus or minus 4 minus x squared, or y squared. I don't know if you want to write all this stuff down. I mean, you can if you want. I'll have it in my notes, but this is a way to show you that this is not the best way to do this, and I would strongly discourage you from doing something like this. What? The PowerPoint, the video. I'm videotaping this also, so it'll all be there. So in any case, I would go through this. If I were doing this, I would have to split the first one up to two different regions. And with respect to x first, I would enter through this region negative square root of 4 minus y squared, and then exit through this region. This region is actually a negative square root of 1 minus y squared. That's the inner circle over here. And then the y limits would go from 0 to whatever this is. I think this is 1 because it has a radius of 1. So I have this for this region. Now I have to consider another region. Maybe I'll change colors over here. And this will give me another set of limits. But guess what? I'm not even done yet, because now I have a third region that I haven't considered yet, because this region switches functions. So, okay. At this point, we're saying that this is too difficult to do in Cartesian coordinates, and that if I were to do this in polar coordinates, I'll probably have an easier time. Okay? So, too difficult. In Cartesian. And the fact that this is a polar coordinate shape probably means that we could be better off doing this in polar coordinates. So what do you remember from polar coordinates? Well, in polar coordinates we have these special functions, transformation functions that go from one coordinate system to another. This other one isn't used so much, but it's still, this is how the transformations are related. So these are equations that we're going to want to remember, and whether you like it or not, you'll probably have it memorized by the end of the semester. So we'll be using combination of polar coordinates in 2 dimensions and then send this up to 3 dimensions. And when you think of polar coordinates or cylinders, cylindrical coordinates, you'll think about these equations. So these are the polar coordinate calculations that we're going to want to do. The other thing about polar coordinates is that the way it's being drawn out is different from Cartesian coordinates. You know, in Cartesian coordinates, we have our graph paper looking like squares. In polar coordinates, your graph paper is a little bit different. Your polar coordinates is based on radial lengths from the origin and angles. And so the grid on your polar coordinates is different. So when we're dealing with double integrals, there's another piece of information that's important to consider when we're switching to polar coordinates. Oh, yeah, so let's redo this in polar coordinates. So in polar coordinates, this circular region over here can be described going from 0 to 1. Your radial distance goes from 0 to 1. And then the angle goes from 0 all the way up to 2 pi. So what do you notice about these limits? They're constant limits. So if you have an equation, or if you have a region that's polar in nature, there's a good chance that your limits are all going to be constants. And I don't know if you've noticed it yet or not, but dealing with constant limits is a lot easier than having to put in functions after you do the first integral. Now the second example is also polar in nature. Before I put out how to describe the region in polar coordinates, you want to take a guess. What do you think our R limits are going to be? What? It starts from 1 and then goes to 2 or 4? 2. It's just the distance here. Okay? So, tricky part, remember that when you're dealing with the radius, this equation of a circle, the radius is going to be the square root of that number that's on the outside. So R is probably going to go from 1 to 2, and theta is going to go from where to where? Doesn't go all the way around to 2 pi, it stops at pi, so we're going to go from 0 to pi. So that is going to provide another, in terms of double integral talk, we're going to have limits of integration that are constants all the way through. Again, we have a region that's polar in nature, and so we're going to come up with nice equations or nice limits that are mostly or all constants. So that makes our calculations for integrals a little bit easier. Now, I was also making a big deal out of the area region. I got ahead of myself. It wasn't time for that slide yet. So the next thing to consider is that area element, which in terms of double integrals is a dA. So think about the changing variables as like a U substitution. Back in Calc 2, or maybe even in Calc 1, we have a function in x, and then somewhere along the line we say, oh, we can't integrate this in x, and so we're going to want to integrate this with y, or with u. And so you change the variables from x to a u. And then say u, let u equal to something, and then we take the derivative and do something with the dx. Well, if you're going to do a change like that with variables, there's going to be some drastic change here too. So we can think about these substitutions as having to change the differential dA. Actually, dA is dx dy. We need to change that into something where we're dealing with our new variables r and theta. So I'm leaving a little bit of space here because when you take the differential switching from one variable to another variable, then there's a derivative that's going to be involved there. Now, this idea of a derivative here is a little bit more complicated than partial derivatives, because with partial derivatives, we have one function and two variables. And so our output comes out to be, we can consider fx or fy. Our function f has two variables, x and y, and so we have those two derivatives. But here, we have our input x and y, and then our output is r and theta. So we're actually dealing with two variables for the input and then two variables for the output. So that gets a little bit more complicated in terms of derivatives. Now, we could talk about the derivatives now, or we could talk about it later if we have time, but in double integrals, we're really just going to be focused on this one special U substitution, so to speak, R theta substitution, if you want to think about it that way. That it's really not worth talking about the general terms. It's really just worth focusing on this particular scenario. So that's what we're going to do. We're going to ignore the idea of this derivative from R2 to R2, which is what's really happening here, and focus on this special case. And to find the differential, the dA, which is an area element, what we're going to need to do is we're going to need to break up our region into sectors, little subsectors. So you know how we broke up our region in our Cartesian coordinate, and then we took a look at one little rectangle here as your r sub I, j, or something from before. This time, we have to look at how our sector is being drawn with polar coordinates, and then with r and theta, and it's being drawn like this. So what we're going to do is we're going to focus on some randomly selected subsector here and try to find the little area that describes that. So we need to find the area of R sub I comma j, or R sub ij, and see what we can do. If you remember the formula for a sector that goes all the way up to the origin, the area is equal to, if you remember what the area was, like 1/2 r theta or something. So r is the radial distance from the origin, and then theta is this angle spanned here, theta. I guess that's a really crappy picture. So I'm going to exaggerate this a little bit. Well, I don't have to exaggerate. I'll just say the area of this little sector, if this is theta and this is r, is 1/2 r theta. Now, before I come up with that formula, this is not a sector from the origin, right? So we can think about subtracting out another piece of this. So we can think about this first one. So the theta sub I or sub j, theta sub j minus 1 is going to be this span of this angle from here to here. And then the Ri sub 2 is this bigger radius. So this first part is really looking at this first cut over here. Now the second one is looking at pretty much the same angle, except you're one short, you're one little subsector short. So you're taking away this bit over here. So what you're going to have left, so what you're going to have left is this area, exactly this area that we're looking for here. Now that we have this equation, let's just do some simple algebra, and distribute and multiply and do all kinds of stuff, factor. So if we factor out 1/2 theta j minus theta j minus 1, we're going to get an Ri squared, Ri minus 1 squared left over. And we see that this is a difference of two squares. We can further factor that out into Ri minus Ri minus Ri minus 1, Ri plus Ri minus 1. So that just takes this and factors that. What else? What else we could do with this is we can consider these two expressions as a difference between two partitions. And so when we have the difference between two partitions, what can we call that? Any ideas? It's the change. It's change in the angle and change in the radius. So we can kind of think about that as the delta theta and then the delta r. So if we take those two values and call them delta theta and delta r, then we have something that's even simpler. Oh, we also want to make one more change. R sub I and R sub I plus R sub I minus 1. If we add those two and then take half of that, that's like taking the average, right? Taking the midpoint. So if you take a look at this point in here, that's a point that's inside of the region. We can call that R sub I star, to be that point in the middle, so we can consider that as a point in the region. And if we make those substitutions along with the deltas, then we can take a look at r sub ij as r sub I star times delta r and delta theta. Now we've kind of seen x sub I star before, haven't we? It's like it's either the left endpoint, the right endpoint, or in 2D it's like the corner or the midpoint, or any point in the region. Here we have the midpoint within that little subsector, so I think that'll work fine as your r. And then when you put that into the double integral and then you do your Riemann sum becomes the integral, that just becomes r, the variable r. So this r sub ij is your area region that you're going to use to change from dx dy. So imagine our dA, d capital A, the differential now changing into dr d theta. When you make that change, this area element is going to produce an extra r. So this area element r sub I theta is going to contribute to our dA change to the dr d theta. And when I say dA, I mean dx dy or dy dx in some order. And then when we change it to r and theta, it's always important that there is this extra r there. So that's like your u substitution. When you take the derivative, the extra r comes out. And so from now on, when we do a polar coordinate change, you're always going to have an extra r. Okay? So that's all there is to remember with that. Always an extra r. So this is the formal theorem from your textbook. You're going from f of xy with a dA. That's going to change into, instead of x, you have r cosine theta. Instead of y, you have r sine theta. And then the dA becomes r dr theta. So we're going to do our substitutions, provided that our limits are going to be nicer than what it would normally be. And then we're going to come up with this new integral in r and theta with an extra r. Okay? So let's do, I had 4 examples in mind, so I'm just going to do 2 of them. And I'll do 2 examples. The first one you have to choose example 1 or example 2. Is 1 better or is 2 better? It's like going to the doctor, right? Eye doctor. 1 or 2? Yeah. You just say, oh, it's 1. 1's better. If you choose 1, your prescription stays the same. If you choose 2, then you have to go. No, I don't know. They change it up too sometimes, I've noticed. All right, let's do example 1. Here is our double integral, and D is the top half of the disk centered in the origin with radius 5. Okay? So we can easily draw that, top half of a disk. Disk just means it's filled in. Radius 5. This means my equation is x squared plus y squared is equal to 25. But I don't even have to write that down, because all I really care about is what are my limits going to be. And what are my limits going to be? What's r going to go to? From where to where? 0 to 5. That's the radius, right? Theta goes from where to where? 0 to pi. Okay, so we're almost done. We got the limits we're going to change the x into r cosine theta, and this is going to be squared. You're going to change the y into r sine theta, and we're going to integrate this from 0 to 5 with respect to r, and then with respect to theta from 0 to pi. And what did I tell you not to forget? The extra r. RDR, R. It's RDR. Okay? Now, I've said to myself that I was going to stop doing integrals, and I'm not going to do this completely, but I want to show you the advantage of having constant limits. Not only constant limits, but in this particular case, you don't have any separate terms that you're adding and subtracting. These are all factors. So if I collect all the terms inside, let's say the r squared, another r, so that's r to the 4th total, cosine squared theta and sine theta. This is essentially your integrand, right? Now your inner integral is taking the integral with respect to r. So in your inner integral, the thetas are constant. So you can imagine taking that outside of the inner integral. So I'm going to do this in steps, and in the future I'm just going to write this in one big move. But the outer integral takes in your inner integral, and then you're taking the theta outside of your inner integral. And your inner integral is 0 to 5. After you take that out, all you have is r to the 4th left over. So you see what I did here? Okay. Now, if I focus on this little subintegral, this has no thetas in it. So this will become constant. Actually is constant after you do the evaluation. This is constant with respect to theta, so I can take that outside of the outer integral. So really what it comes down to is that I have two separate integrals to take. And then I just multiply them. If you're adding or subtracting, this is not going to be so easy. So you just have to be careful with when you can do this. So from here, next time I would just collect the r's and integrate that separately, collect all the thetas, integrate that separately, and then multiply my results. I'm still not going to do this integral, but this is easy enough, right? All right, so that's the first example. We're going to skip through the second example. Now we're going to do the third example, or 3 or 4. Which one's better, 3 or 4? It's meant to be 15. Okay, 4. So, I still have to see my eye doctor about contacts and stuff. Okay. Now, this is an example where if you were to try to flat out do this by hand, you're not going to be able to. And if you were to punch it into Wolfram Alpha, they might give you some weird answers and stuff, introducing new series functions. And we talked about those functions that can only be defined by series. So instead of dealing with that, we can notice that the region, I don't know if you can see the region right away, but the region looks like it might be polar. And some of the hints that might be polar is that this is a square root of 9 minus x squared. So it looks like if that's y is equal to that, then it might have something to do with a circle. Before I go on to that circle bit, if I'm switching integrals, I have to see what the region actually looks like, right? So my inner integral is y, and I can define my y limits here. Y goes from 0 to the square root of 9 minus x squared. And again, if you take the time to look at the relationship when you have y is equal to 9 minus x squared, think about squaring both sides, and then you'll have x squared plus y squared is equal to 9. And your x limits go from -3 to 3. So your task here is to take a look at this and say, hey, that kind of looks like a polar. And then when you convince yourself of that, your y goes from 0 to the top half of the semicircle of radius 3. And then your x goes from -3 to +3. So it looks like it would make sense for this to be the region, the top half of the disk of radius 3. Now that you know that, let's see if we can transform this into polar coordinates. I don't know if you would, I would probably have a hard time getting my polar coordinates just by looking at the limits of integration. I actually need to draw it out to see what's going on. Now that it's drawn out, this part is going to be really easy. R goes from where to where? R goes from the radial distance from 0 to 3, and then theta goes from 0 to pi. So now our integral is a sine of x squared plus y squared. I think that's just r squared, right? Based on our polar coordinate substitutions, x squared plus y squared is equal to r squared. So that comes down here. And then now we're going to integrate this with respect to r first, going from 0 to 3, and then with respect to theta, going from 0 to pi, and then don't forget the extra r. Now without doing this integral, can you do this integral? What would you do? How would you integrate this? U sub r squared, and there's an extra r to cancel. We didn't have that luxury up here with Cartesian coordinates. But now this becomes a lot easier. By the way, I'm not adding or subtracting any terms here, and these are all just products. And I can take the theta out. Wait, there is no theta. There's a 1 theta. But I know the integral of theta, integral of 1 d theta is just theta. Theta from 0 to pi is just going to be pi. So already that outer integral, if I could do that separately, I'm already done with that. And so you just need to figure this out with a u substitution. Okay? So that makes polar coordinates really easy to work with. Any questions? All right. So when the honor students are doing their presentations, they're going to do this for only half of the class, and then they're going to hand out a worksheet for you guys to work on. So I have a worksheet for you to work on. So it's not just about watching the presenters, it's actually doing the work. And I can stop this.